AI progress is moving beyond simply adding parameters. Models are gaining depth through reuse, learning to justify answers with pixel-level evidence, and carrying longer histories into physical action. That matters because the next bottleneck is no longer raw competence, it is stability, verifiability, and reliable behavior over time. This week's results show looped transformers becoming more trainable, Gemini 2. 5 Pro still struggling to prove what it sees, and NVIDIA's GR0T gaining longer horizon control through test time learning. We'll unpack what this reveals about the next scaling laws for models and machines. Let's explore the first paper, Deep Loop Depth Scaling for Looped Transformers. Deep Loop, from researchers at Princeton University and UCLA, addresses a stability problem in looped transformers where a small set of physical blocks is revisited to create greater effective depth without storing new parameters. The authors show that shared residual updates are both aggregated across visits and reread across visits, producing a visit alignment factor that standard deep norm analysis misses. In the worst-case aligned regime, the required scaling exponent rises from 0.25 to 0.5, leading to the parameter-free post-ln rule. Alpha equals 2n, 0.5, and beta equals 8n, 0.5. On OpenAI's GPT-2 small and GPT-2 medium backbones trained for 50B tokens on FineWeb Edu, Deep Loop is neutral at 1 loop and improves validation loss as recurrence increases. At GPT-2 medium with 7 loops, it reduces loss by 0.0278 nats relative to the baseline. The method also improves the 8-task LM evaluation harness average, reaching 55.2% in the one-shot GPT-2 medium setting at 7 loops. Applied to the hierarchical reasoning model on ARC, AGI 1. Deep Loop raises 2-vote accuracy from 36.5% to 39.75%. The experiments used NVIDIA H200 GPUs and a small GPT-2 exponent sweep found reliable training only at 0.5 or above, supporting the theoretical threshold. Let's explore the second paper, Evidence-Backed Video Question Answering. Researchers from Salesforce and Brown University introduced evidence-backed video question answering, or EVQA, which requires a video LLM to output not only an answer, but also supporting time segments and dense, tracked pixel masks called masklets. Their human-verified ST evidence benchmark contains 1,298 questions for multiple-choice grounding and 2,706 questions for generative grounding, with masks annotated at 6 frames per second. It draws a sharp distinction between knowing an answer and proving it visually. OpenAI O3 and Gemini 2, 5 Pro can achieve strong QA, while spatial grounding remains inconsistent, and many open-source systems perform near the 25 random baseline in mask selection. The authors also released ST Evidence Instruct, a 160K scale instruction tuning dataset built through automated pipelines combining Qwen 3, VL, Gemini 2, 5 Pro, and Samtray. Fine-tuning unipixel-based models with LoRa produces major grounding improvements over size-matched baselines. The 7B model gains 27.2 t-mean points for temporal evidence and 13.8 J and F points for spatial evidence, while QA accuracy rises only modestly. On the multiple-choice benchmark, Gemini 2 5 Pro reaches 82.82 QA accuracy, but its 44 J and F generative spatial score shows that semantic competence does not guarantee dense visual justification. The central conclusion is that scaling alone cannot close this perception reasoning gap. Aligned evidence data, integrated objectives, and architectures that jointly reason over time and pixels are necessary for explainable video understanding. Let's explore the third paper, RoboTTT Context Scaling for Robot Policies. RoboTTT, from NVIDIA researchers collaborating with Stanford University and the University of Texas at Austin, adds test time training to NVIDIA's GR0TN1 7 robot foundation model, replacing a conventional recurrent state with fast weights updated by gradient descent during both training and deployment. Its 2-layer MLP fast weights compress long visual motor histories into parameters, while sequence action forcing and truncated backpropagation through time make training feasible at 8K time steps without increasing inference latency. On YAM bimanual robot assembly tasks, RoboTTT reaches a 79% average task completion score versus 42% for the single-step GR 0T-N1 7 baseline, an 87% improvement, and it is the only evaluated method to complete the 5-minute, 10-stage Gearbot task, succeeding in 2 of 10 trials. Scaling pre-training context from 1K to 8K time steps raises closed-loop performance from 43.9% to 71.5%, a 63% gain, showing context length as a new scaling axis. Long context conditioning also enables one-shot imitation from a single human video, with 6 of 10 circuit trials fully successful, while the recurrent GDN baseline achieves 0 of 10. Finally, dagger distillation uses failed robot actions as context and human corrections as targets, producing a 36% improvement for RoboTTT and enabling on-the-fly recovery from execution errors. That's a wrap on today's AI paper highlights. Thanks for watching.